Hi everyone. So in this video, I'm going to talk a bit about the different kidney function tests, sort of what they tell us, when they can be used, and why they're significant. And so I want to split up the kidney function tests into two types of tests. The first type of test is tests for GFR, or glomerular filtration rate, and the second type of test is tests for tubular function. And this is going to be particularly important when we're trying to assess whether a kidney injury is a pre-renal kidney injury, in which sort of GFR is affected, or a renal kidney injury, so a tubular injury, in which just tubular function is impaired, but GFR is actually intact. And we're going to see how these play out in our different kidney function tests. Okay, so first, in order to talk about the kidney function test for GFR, we need to start off by understanding the concept of clearance. So let's talk about clearance. So clearance, remember, is defined as the amount of blood completely cleared of some solute in a given amount of time. So clearance has the units of milliliters per minute. So it's how much blood, or how much of our fluid, is completely cleared of a solute in a given amount of time. So it has the units of milliliters per minute. And the question is, why do we evaluate our, why is this a useful quantity to think about, right? Why do we think about the amount of blood completely cleared? Why not just ask ourselves, if we're interested in how much stuff is getting excreted, why not just ask ourselves, how much stuff is getting excreted in the urine, how much stuff per minute, osmoles per minute, moles per minute, whatever. And the answer to that is because the way that our body works, the way that our body actually clears out things, is it clears out things using fluid, right? So, our kidney filters a certain amount of fluid, and that fluid then gets processed. There's, reabsorption, secretion, so on and so forth. And so, but our kidneys work in clearance. And so what does that mean, sort of mathematically speaking? Well, so imagine we start off with some fluid that, has a certain amount of solute in it. And there's some concentration of solute in here. And, it makes one pass through the kidney. And, there's a certain clearance. So let's say, this is a 5 milliliter solution. And let's say 1 milliliter gets cleared every minute, right? So basically, effectively, 1 milliliter of this solution loses all of its solute per minute. Now, that does not mean that we actually lose 1 milliliter of fluid. So it's not that we're getting rid of this fluid here. Instead, what's happening, remember, is 1 milliliter worth of fluid is getting cleared of solute. So there's no longer solute in that fluid, but that fluid may get reabsorbed. And in fact, our body's often reabsorbing most of the fluid and just secreting whatever is kind of in there. And so what we might end up having is a scenario in which we have 5 milliliters of fluid, but we have, since we've cleared 1/5 of it, we only have, the solutes from not this last fifth. So sorry, I didn't do a good job of drawing this, but this last fifth is now cleared, and we have the same solutes as before in the rest of our solution. So now, so we've cleared basically 1/5 of our solute, and now let's say this gets recirculated, so this gets all mixed up, and now all of this solute is now mixed up throughout the fluid, and we come back to the kidney. And so the kidney now clears another 1/5 of this, but remember, this has rehomogenized. So it's not like we're clearing another 1/5, from our initial solution, right? This is 1/5 now of this more dilute solution. And so we're going to keep taking 1/5 out every time we go through the kidney, let's say. And so effectively what we're going to do is we're going to dilute this, but we're not going to dilute it in a way that's just cutting out until we have nothing. Instead, we're going to dilute it, and then we're going to dilute it, and then the solution itself is going to get more dilute. And then we're going to take a fraction of that, and it's going to get more dilute. And so, in fact, clearance works not in linear decay, but it works in an exponential decay fashion. And you can kind of appreciate that, by this sort of serial dilution effect. And so that's kind of the difference. That's why we kind of think about, that's why we use clearance, because mathematically what's happening this process is fundamentally, this is what's happening in our kidneys, right? So if we just, put a bolus of something in our blood, the way that it would get cleared is an exponential decay, and we might not decay to zero. If we're producing this stuff, then we might actually decay to some steady state concentration, which is above zero. But the bottom line is that it's an exponential phenomenon, and that clearance, this concept of clearance is very closely associated with exponential decay. That's the mathematics of clearance. Exponential decay. Okay. So now that we've understood clearance, how can we use it in a sort of physiological context? Okay, so the way that we're going to use it for renal function tests is that GFR is approximately going to be equal to our creatinine clearance. Okay, and so let's understand this. So in order to understand this, let's make a quick diagram of our glomerular apparatus, or let's do our vascular apparatus in the kidney. So this is kind of different than how we usually depict the kidney as sort of the urine apparatus or the tubular apparatus. We're going to depict now the vascular apparatus. So this is kind of our glomerulus over here first. This is glom. And then let's say we have our sort of tubular capillaries or vasa recta network over here. And then we end up and we come out into our renal vein over on the other side. Okay, so in order to understand why GFR is equal to creatinine clearance, we have to understand that what functionally is happening to creatinine in the kidney. So creatinine in the kidney is getting filtered in the glomerulus. So whatever, there's some filtrate. Remember, there's some fluid coming out of here. And along with that fluid, we get some of our solute. And effectively, for all intents and purposes, whatever stuff is filtered out along with the water in the initial filtrate, that stuff goes into our urine over here. So remember, this is the luminal side. This is the lumen over here. And so whatever stuff gets initially filtered, most of that stuff is not getting reabsorbed. There is a little bit of secretion that happens with creatinine, so there is a little discrepancy between GFR and creatinine. But since all of the, if we think about, remember, clearance being how much fluid is being cleared of solute in a given amount of time, the amount of fluid that's coming out of here, remember, the amount of fluid that's coming out, that's equal to our GFR. So if we ask the question, how much fluid is being cleared of creatinine as we move through our vascular system in the kidney, the answer is the amount of fluid being cleared is equal to the GFR, because whatever GFR comes out, that's how much creatinine is being cleared. So whatever GFR comes out that's equal to the amount of fluid that's being cleared of creatinine. And remember, that fluid can get reabsorbed ultimately, the water in that fluid, but the creatinine stays. And so it's this relationship holds. GFR is equal to creatinine clearance. Okay, so now that kind of brings us to our first renal function test. So if we're looking at tests for GFR, the first test is going to be creatinine clearance. And how can we measure creatinine clearance? Well, we can say, remember, clearance is how much fluid is being completely cleared of creatinine per given time. So we can ask ourselves how much creatinine is being excreted. So that number is going to be equal to urine creatinine the urine concentration of creatinine times the volume of urine. So remember, this numerator is equal to how much CR is excreted per minute. And we divide that now by our plasma creatinine, our serum creatinine. And that's, what's the concentration of creatinine in the plasma, right? And so that tells us, if we divide how much is being excreted, so we say, 5 osmoles per minute are being excreted, or 5 millimoles per minute are being excreted, then and our plasma creatinine is a certain amount, then the ratio of these two is going to give us how much fluid is being cleared of creatinine, right? So our plasma creatinine tells us what's the concentration of creatinine in the plasma, and so if we tell how much stuff is being excreted per minute and we divide that by the concentration, we get how much volume of fluid is being cleared per minute. And you can do the units in your head if that's confusing. But the bottom line is this formula will give us creatinine clearance. And remember, creatinine clearance is approximately equal to GFR. Okay, so what happens if we don't do a urine, let's say we don't measure any urine, we don't do any urine studies. The second sort of shorthand that can be used is serum creatinine. So how can serum creatinine be used to estimate GFR if we're not measuring urine creatinine? So this is true in all circumstances. This first relationship, creatinine clearance is always going to approximately be equal to GFR. Now, if we make a steady state assumption, and this is where we have to assume here steady state. So assume steady state. So if we make that steady state assumption, then what we can assume is that the production of creatinine is equal to the excretion of creatinine. And remember, that's the numerator in our creatinine clearance, right? So if we say GFR, if we write this up here as GFR is approximately equal to this, excretion of creatinine. Okay, so if we say that production is equal to excretion in steady state, right? So whatever is being produced is being excreted if we have a constant amount in our body. And so if we make this steady state assumption and we make some assumptions about how much creatinine is being produced. So say, we have some estimates of muscle mass, or we have some estimates of, on average, some person, we have some predictors that can enable us to say how much creatinine do we kind of hypothesize that this person is creating. Then we can make a prediction for the excretion if we assume steady state. So now what the equation becomes is GFR is approximately equal to excretion on the numerator, which is now approximately, remember, production of creatinine over serum creatinine or plasma creatinine. And, now what basically we can say is that if our plasma creatinine is high, right? So if we assume production is constant, or we assume that there's some value for the production that's kind of, approximately constant amongst people, then if our creatinine is high, then our GFR must be low. And that's kind of the fundamental way in which we can interpret serum creatinine as an indicator of GFR in the context of a steady state assumption and some assumptions about the production of creatinine. Okay.